If you,
Yeah.
yeah, this is a high quality hockey puck, obviously. See, clearly indicated, life-size model. Nailed it. If you draw an accurate picture, that's one of the most important parts so that you can see clearly what's going on here. By reading the problem, you see that the puck has a mass of 0.6 kilograms, initially sliding at 15 meters per second. It's going to strike a 2 kilogram block of ice, that's the large square looking thing there, which is initially at rest, but after the collision it's moving 4 meters per second. So here I have the mass times velocity of the puck, colliding with the mass times velocity of the block that's at rest. That momentum before will equal the momentum after, which is the hockey puck times the velocity we're looking for, times the mass of the puck, the block, which is still 2 kilograms, now moving at 4 meters per second. So if you just do m times v for each thing, once you have it set up, it's really just solving algebra here. So you've got 0.6 times 15 plus 2 times 0 equals mv, that's 0.6 times v, we're looking for that velocity there. And again, you can put in all the units if you want to.
Did you do anything with the 5 meters per second like this is before?
Not yet, we're just going to do part A, but then we're going to change one thing and see how that affects our answer. So for part A, we're just leaving the velocity at 4 meters per second, but in part B, we'll then say what if the block we're sliding at 5 meters per second. So we're going to do A and then we'll do B. So if you just do mass times velocity for each thing, we have 9 plus 0 equals 0.6 times v plus 8. Subtract 8 from both sides. 1 kilogram meter per second equals 0.6 times v. We can find the velocity about 1.66, 1.7 meters per second. All right. So what that means is after the puck collides with this block, it sends the block moving at 4 meters per second, and now the puck's not going 15 meters per second anymore, it's only going 1.7 meters per second. And that was for part A. So how would part B be different? Okay, so if we change the velocity to 5 meters per second, now over here, when we do mass times velocity, we don't have 8, we have 2 times 5, we've got a momentum of 10. So here we've got 9 kilogram meters per second plus 0, 0.6 v, just like we did before, plus 10 kilogram meters per second. So now when we subtract 10 from both sides, we get a negative 1 kilogram meter per second. And so our final velocity, when we take negative 1 times 0.6, is negative 1.7 meters per second. Now that's the same speed that we just got a moment ago. This answer, however, is negative. What's the difference if our answer is positive or negative? What is the puck doing now that it wasn't doing before? It recoiled. It's now going backwards. Now instead of hitting the block of ice and still going forward, it hit the block of ice and now it's going backwards. Conservation of energy with collisions. The only time that energy is conserved in collisions is if you have a 100% elastic collision, which typically only happens with particles. Momentum is conserved in all collisions, whether they're elastic or inelastic collisions, you have conservation of momentum. If you should have a 100% elastic collision, you could come up with a conservation of momentum equation and a conservation of energy equation with the kinetic energy before and after equal. You would have two equations, and you could solve for two unknowns, and you could find two final velocities. We're not actually going to have time to do examples like that, but you could actually come up with a conservation of momentum equation, a conservation of energy equation, substitute one in for the other. It's loads of fun. But rather than doing one like that, let's look at one more inelastic collision. I'm gonna draw this up on the board.